Hello everyone, I'm Jiandong Wu from the School of Materials Science and Engineering, Southeast University. The topic I report is the characteristics evaluation of an ultra-high strength and high ductility cementitious composites incorporating waste glass powder. My report consists of 4 parts. Concrete is a brittle material. With the increase of strength, the brittleness of concrete performance is more obvious. When a strong earthquake or military strike occurs, concrete is damaged, which seriously affects the safety of people's life. The durability of concrete is also a problem that can't be ignored. As we all know, UHPC is famous for its super high strength and high durability. However, the tensile strength of UHPC is generally low, which still can't resist the damage caused by strong vibration. In recent years, THDCC is developed. This is a new type of fiber-reinforced cementitious composites. It's famous for its ultra-high tensile strength and high toughness. However, THDCC uses PVA fibers. This fiber is a hydrophilic fiber, which is generally used to prepare low-strength matrix. Therefore, the compressive strength of THDCC is low. Based on these two materials, UHS-HDCC is developed. It refers to a special fiber-reinforced cementitious composites with compressive strength greater than 120 MPa, tensile strength greater than 3%, and shows strain hardening behavior and multiple correcting characteristics. The excellent performance of UHS-HDCC makes it have better potential when it is used to resist high vibration building. UHS-HDCC is mainly used in antiseismic node, anti-blast structure, bridge deck pavement, high-rise building. Table 1 shows the main mixing ratios for preparing UHS-HDCC and THDCC at present. It can be found that the cementitious contains cement and silica film, and the amount of cement is more than that in THDCC. The production of cement produces PM, which causes environmental problems. Waste glass has brought some troubles to the society, such as stacking occupied farmland, non-biodegradable, high recycling costs. Being amorphous and containing large amounts of silicon, glass should be an excellent pozzolanic material for concrete industry. Therefore, when glass is finely grounded to powder, in theory, it could be used as partial cement replacement. Of course, glass also has a very high amount of sodium oxide, which is a source for alkali-silica reaction. However, there have been research reports that with glass powder with a particle size of less than 75 microns basically remove the negative effects caused by ESR expansion. Therefore, it is a feasible solution to use with glass powder instead of cement to prepare UHS-HDCC. Here are the characteristics of the raw material. The mixing ratio of the matrix is calculated according to the tightest packing theory of particles. The smaller the ISS, the more compact the particles of the matrix. This is an experimental test method, including compressive strength test, uniaxial tensile test, and a single fiber pull-out test. This is a result and a discussion. Figure 8 shows the fluidity of fresh UHS-HDCC mixtures with fiber or without fiber. It is important to note that the added WGP has a positive effect on the fluidity of fresh UHS-HDCC. However, PE fiber has a high aspect ratio and a large curvature, which has a serious impact on the fluidity of the matrix. The damage to fluidity is inevitable to meet the high ductility of the ultra-high strength matrix. However, the fluidity of the fresh fiber mixture with WGP is slightly improved. The change of it may be attributed to the smoother surface layer and nearly non-absorbability of WGP. Figure 9 shows the effect of WGP on the compressive strength and the flexural strength of UHS-HDCC at different curing ages. The pH value of the pore solution improves the dissolution rate of WGP. It can be found that 15% WGP has a positive effect on compressive strength and flexural strength. Figure 10 shows the effect of WGP on the tensile performance of UHS-HDCC. All samples showed strain hardening characteristics and multiple correcting behavior. The initial cracking tensile strength and ultimate tensile strength of UHS-HDCC reached the maximum at 15% WGP, and then decreased with the increase of WGP. The single fiber pull-out test is essential to determine the fiber and the matrix interaction properties, which describes the micro-mechanical features of UHS-HDCC and build a relationship with the micro-tensile strain capacity. The embedded length of fiber is 6. The fibers were damaged after extraction. There is no fracture. All fibers showed strain hardening during the pull-out process. In addition, due to incorporation of WGP, different degrees of damage occurred at the fiber pull-out end. Fig 14 presents the frictional bond stress and slip hardening coefficient between the fiber and the matrix. When WGP content is 15%, the maximum of the frictional bond stress was 1.96 MPa. The large friction bond strength represents the large load required in the tensile process. It can be seen from Figure 15 that the maximum fiber bridging stress has occurred in the specimen of WGP 15% and then tends to decrease when the WGP content exceeds 15%. The last part, conclusions. The introduction of WGP improves the fluidity of UHS-HDCC. The compressive strength, flexural strength of UHS-HDCC were improved by adding 15% WGP. All the UHS-HDCC specimens exhibited an obvious tensile strain hardening phenomenon and a uniform distribution crack. Particularly, the ultimate tensile ductility of UHS-HDCC reached 6.62% when adding 14.5% WGP. All the single fiber force displacement curves of UHS-HDCC specimens exhibited a slightly slip-hiding behavior. The fiber and the matrix interfacial average frictional bond stress tends to increase first and then decrease with the action of WGP. Thank you for your attention.